All right, let's jump right in. Today, we're going to break down a really fundamental tool in algebra, partial fractions. This is a technique that lets you take one big, messy fraction and split it into a bunch of simpler, much friendlier pieces. Trust me, it's a total game changer, especially as you get into more advanced math.
So here's the game plan for today. We're going to start by looking at something you already know how to do, but we'll flip the script. Then we'll lay out the rules of the game, tackle the two most common scenarios you'll run into, and then we'll wrap things up with a typical exam question to see how it all comes together. So, to really get what partial fractions are all about, let's start with a process you're probably pretty comfortable with, adding fractions. But we're going to come at it from a totally new direction. You know the drill, right? If you've got a couple of simple algebraic fractions, combining them is no big deal. You find a common denominator, you do the multiplication, you add the numerators, and you end up with one more complicated fraction. Easy peasy. Okay, but here's the real question. What if I gave you that big fraction on the right? How on earth would you figure out that it came from those two simpler pieces on the left? That whole process of working backward, of deconstructing the fraction, well, that's what we call partial fraction decomposition. And it is absolutely crucial, especially when you hit calculus. So, how do we actually do this? How do we know how to split a fraction? Well, the secret, the entire roadmap, is hiding in the denominator. The kind of factors it has tells us exactly what method to use. It's kind of like a diagnosis. You have to look at the denominator first before you can prescribe the right treatment. And this whole process, this magic trick, it has a name: partial fraction decomposition. The goal is always the same. Turn one complicated thing into a sum of simple things. Because let's be honest, who wants to work with the complicated version when you can have simple ones? If you crack open your textbook, you'll see a few different scenarios for that denominator. It might have unique factors, it could have a repeated factor, or it could even have a quadratic one. We're going to really nail down the first two today to build a super solid foundation. All right, let's tackle our first case. This is kind of the classic, the one you'll see all the time. It's what we do when all the factors in the denominator are unique. They're all different. Okay, here we go. An example right out of the textbook. First things first, you've always got to look at that denominator. We see two factors, 2x plus 1 and x minus 3. They're linear and they're distinct. They're not the same. That's our signal that we're in case 1 territory. Now, no matter how tricky these problems look, the game plan is always the same. Just 3 steps. First, we write down what the answer should look like using some unknown constants we'll call a and b. Second, we do a key algebraic move to get rid of the fractions. And third, we solve for those mystery constants. Getting this set up right is absolutely crucial. Each unique factor gets its own fraction with a constant on top. So we have a over 2x plus 1 plus b over x minus 3. Then we do this one awesome algebraic trick. We multiply the entire thing by the original denominator. That wipes out all the fractions and leaves us with one core equation to solve. Okay, so once we have that key equation, we've got two main ways to solve for our mystery constants, a and b. Substitution is kind of like a clever shortcut. Equating coefficients is the more methodical, surefire way that always works. You can pretty much pick whichever one feels easier for the problem you're looking at. This is where substitution is just so smart. See that a term? It's being multiplied by x minus 3. So what if we just make x equal to 3? Poof! The whole a term disappears, leaving us a super simple equation to find b, which turns out to be -1. We can do the same thing for the b term. To make it disappear, we just set x to -1/2, and we can solve for a just as easily. We find a equals 4.
Okay, so that's one way. The other method is equating coefficients. What you do here is you multiply everything out on the right-hand side. Get all your x terms together and get all your plain old number terms together. Then you just match them up with the left side. So a plus 2b has to equal 2, and -3a plus b has to equal -13. That gives you a pair of simultaneous equations, which you can solve to get the exact same answers for a and b.
So we found a is 4 and b is -1. All we have to do now is pop those numbers back into the form we set up at the very beginning. And boom, there it is. We've successfully broken our big fraction down into its simpler parts.
All right, you've got case 1 down, but what happens when things get a little repetitive? I mean, what if a factor in the denominator is squared or cubed or raised to some other power? Well, this is what we call a repeated linear factor, and it's our case 2. Now listen up, because this is the single most important rule for this case. It's where everyone messes up. If you have a factor like ax plus b squared, you need to account for every power of that factor. That means you need a fraction for the factor to the power of 1 and a fraction for the factor to the power of 2. If it was cubed, you'd need 3 fractions. Don't forget the lower powers.
Okay, let's put this new rule into action. We've got this new problem from the textbook. The denominator is x minus 4 squared. You see that little squared symbol? That's our giant flashing sign that says, hey, this is a case 2 problem.
And just like before, getting the setup right is half the battle. So, following our big rule, we need a piece for x minus 4 and another piece for x minus 4 squared. From there, the process is exactly the same. We multiply by the original denominator, x minus 4 squared, to get rid of the fractions, and that leaves us with our new key equation. 2x minus 11 equals a times x minus 4 plus b.
Okay, time to solve for a and b. Well, the most obvious move is to make x equal to 4, right? That completely wipes out the a term and gives us b straight away. We find b is negative 3. But then what? We can't use that trick again to find a. No problem. We just pick another easy number, like 0. We plug in x equals 0 and our new value for b, and that leaves us a simple little equation to solve for a, which turns out to be 2.
And just like that, we're done. We take our a equals 2 and b equals negative 3, plug them back into our setup, and we've got our final answer. The original fraction is now split into its 2 parts.
All right, we've covered the theory for the 2 main cases. Now let's put it to the test with a real-deal exam-style question. These sometimes have a little twist at the start, so you've got to be on your toes.
So check this out. The denominator x cubed minus x, wait a minute, that's not factored. This is the classic exam trick. Your first impulse might be to start setting up a's and b's, but hold on. The very first step is always to make sure that denominator is factored as much as possible.
So remember, your first job is always to factor that denominator completely. First, you can pull an x out of both terms. That leaves you with x times x squared minus 1. And hey, that's a difference of 2 squares, so it factors again into x times x minus 1 times x plus 1. And once you've done that, you look at it and go, this is just a case 1 problem, but with 3 factors. So you set it up with a, b, and c and substitute 0, 1, and negative 1 to find them. So if you follow all the steps, you'll find a is negative 1, b is 3, and here's the interesting part. C turns out to be 0. And that's totally fine. It happens sometimes. It just means that the 1 over x plus 1 piece wasn't actually there to begin with. So our final answer only has 2 terms.
So, after all that algebra, you might be asking, why? Why do we care about breaking fractions apart? Well, here's the payoff. In calculus, trying to integrate that one complicated fraction on the left would be a nightmare, but integrating the sum of the simpler fractions on the right, that's incredibly easy. Think of partial fractions as the key. It's the key that unlocks an entire world of calculus problems. It takes something that looks impossible and makes it simple, and that's a pretty powerful tool to have.